Everyone, I'm Himanshi Dhawan, and the topic of my presentation today is the study of physical mixtures of iridium and metal oxide supports for water splitting applications. As already stated, hydrogen, a chemical fuel, is being touted as the fuel of the future that can be produced from both renewable and non-renewable resources. With only water and energy as byproducts, it can lead to the development of a zero carbon society. Hydrogen, unlike coal and petroleum, is not the primary source of energy, but in fact an energy carrier. This means that it is generated from other resources such as solar, wind, hydro, and even coal, and then stored for the future use. It has the potential of converting intermittent renewable sources of energy into storable chemical fuels. One of the most green ways to produce hydrogen is with the use of a water electrolyzer, which is an electrochemical device that splits water into hydrogen and oxygen. There are different kinds of water electrolyzers, but one of the most mature technology available to us is the acidic water electrolyzer, the diagram of which you can see towards the right-hand side. It basically consists of three main parts, which is a cathode, an anode, and a membrane that permits hydrogen passage. However, because of the acidic nature, it also involves high cost of material and requires corrosion resistant material in use. The water electrolysis can basically be divided into two parts. The first is hydrogen evolution, and the second is oxygen evolution. Hydrogen evolution is pretty straightforward. However, oxygen evolution reaction requires the transfer of 4 electrons, which makes it a more complicated process. Based on our literature survey, we found that the use of a proper catalyst can solve the problem of oxygen evolution reaction. One of the catalysts available is iridium. It is highly active and also corrosion resistant. However, we cannot use it for commercial applications. This is primarily because of the high cost of iridium catalysts. To solve this problem comes in the role of supports. Support is basically a metal oxide on which iridium active metal can be deposited so that it ensures higher dispersion. Now, the mixtures of catalysts can be divided into two parts: physical mixtures and interactive bi or multimetallic catalyst. Physical mixtures are already synthesized iridium and metal oxide supports that are not synthesized together. In contrast, interactive bimetallic catalysts are synthesized together. The objective of my study was to compare the activity, stability, and charge transfer resistance of various physical mixtures and evaluate whether electrochemical cycling of the physical mixture leads to self-organization or redeposition of the active metal on the support. So basically what we did is we took iridium oxide, we took different kinds of supports, it underwent electrochemical cycling, and then we observed whether it did get deposited on the support, whether there were any electronic interactions. To accomplish that, we used a rotating disk electrode setup, which is basically for the ease of testing and has no mass transfer limitations. And the evaluation criteria was enhancement of electrochemical surface area, enhancement of activity, and reduction of charge transfer resistance. The electrochemical surface, what we observed was that there were none. No interactions that point towards any increase in electrochemical surface area or activity based on the electrochemical activity for different iridium oxide and support mixtures. And hence we studied that over a long time during the electrochemical cycling. And in conclusion, we found out that despite rigorous electrochemical preconditioning and electrochemical cycling, during the experiment, no interactions between physical mixtures were observed. This proves that electronic interactions in bimetallic iridium oxide metals can only be produced when there are interactions at the synthesis level. Electrochemical cycling cannot create synergy. While the test showed that there was no electronic interaction in physical mixtures, it was really important to study that because it forms the baseline study for detecting electronic interactions in supported catalysts synthesized by different methods. While electronic interactions were not present excuse me, in physical mixtures, it becomes imperative to detect them in other bimetallic catalysts. In the greater scheme of things, studying electronic interactions in supported catalysts paved the way for improving their activity and stability, thereby aiding the commercial use of this alternate source of fuel.